Hello and welcome to this year's TecQuipment Student Competition award ceremony for 2024. We wanted to thank all the teams and institutions who entered this year. Doing this work alongside your studies will hopefully have paid off, and with one of your teams walking away with £1,150 in prize money. This year it was a very tight race for the winner, with only 2 points separating the winners and the runners-up. But before we announce who the winner is, I wanted to go through a few points and some feedback. So the videos that went well, they clearly described the objective of the study. They ran through the experiments set up and they clearly demonstrated the equipment and experiment clearly. The theory that was used was validated, and we all know in engineering, validation is one of the key concepts. They provided tables and charts, but talked through what they meant, making it really easy for the viewer to understand. And lastly, they were concise, but covered the 4 key criteria areas. They had a research question, experimental design, they showed the experiment being either set up or demonstrated, and then they critically analysed and evaluated the results. And this made an effective presentation. We also wanted to provide some feedback for improvement, because like everything, how can you get better without feedback? So the feedback in general for the videos presented were: have more visuals of the experiment. This makes a better presentation. Even if this meant a short video and then you talked around what was actually being seen, or a photo and a few little bits of the setup, or even pictures and diagrams. If you have a still image, talking around what the viewer can actually see will make it very clear. An explanation of results. If you have a table and a graph, perhaps have these on the same slide. This way, the viewer can see the results and see the charts and make that clear comparison. This makes it easier for the viewer to get and understand what you have done in one easy way. Lastly, a voiceover to explain the results is beneficial, especially when there is a lot to see and read in one go. Having this voiceover, again, makes it a lot clearer for the viewer to clearly understand what you are trying to present. So that is the general feedback that we have found and given this time, in the hopes that if you submit your videos next year, they can be even better. Or if this is your first time, you can use this feedback and use the top tips from the good videos to submit one winning video. So, next up, we're going to have the 2 universities or colleges and their winning videos. So these are the 2 videos competing for the overall title of winner.
This is our TecQuipment Student Competition submission for analyzing heat exchangers. Our team is Josie Kramer, Lance Wolfram, and Elijah Whittington. We are all mechanical engineering students at the University of Michigan Flint. So background is that linear heat conduction is thermal energy transferred through a substance along a straight path. In an experiment, it can be used to calculate heat transfer and heat loss along a path. Thermoresistance describes the ability of a material to conduct heat and is an analog to electrical resistance. At the top, we have the equation for thermoresistance and for heat transfer, which can be written in terms of thermoresistance, and on the left are a couple of pictures that describe these concepts. Our proposed research question is: how does thermoresistance affect heat transfer when using 2 bars instead of 1 bar during a linear heat conduction experiment? We used a TD1002A machine to run our experiment, where we were able to swap out this middle piece here and put in a single solid bar of aluminum and 2 individual bars of aluminum. We were able to read the temperatures using the thermocouples and adjust the power here using the dial. Here's a picture of the casing with the solid bar of aluminum in it and the thermocouples attached and the 2 separate pieces of aluminum in front of it. To set up our experiment, we used a TD1002A machine, which can be seen in the picture. It also diagrams the experiment and the thermocouples here. We used powers of 10 watts, 12.5 watts, and 15 watts. The material we used was aluminum. For one piece, it was 45.75 millimeters in length, and for 2 pieces, it was 22.876 millimeters in length each. All of the diameters were 30.07 millimeters, and there was an ambient temperature of 20 degrees Celsius. Here is a video of our experiment. Here are our results. This table shows the heater power and the temperatures at thermocouples T1 to T3. Here are the results for 2 pieces and for 1 piece, where we highlighted T3 to T5. Here are the results in a table for the estimated heat loss percentage, and this is for a solid piece of aluminum on top and 2 pieces on the bottom. Here are some computations for heat transfer for 10 watts. You can pause here to look more into the computations that we did. This shows the solid piece of aluminum results, whereas the distance from T1 increases, the temperature decreases, and this is about a linear relationship for the solid piece of aluminum. And for the 2 pieces, you can see that as distance from T1 increases, the temperature does not increase linearly because of the 2 pieces of aluminum. It begins to decrease, and then here it experiences a drop from T3 to T5 in temperature because of the 2 pieces of metal where they meet, and then it continues to decrease almost linearly after that. We calculated the thermal resistance here, which contributes to this big drop in temperature. In conclusion, we can say that, as we expected, there's a greater change in temperature between T3 and T5 when using 2 middle section pieces compared to 1 middle section piece. The given temperature changes, you can use that to find thermal resistance at the point of contact with the 2 pieces of aluminum, and we can say that thermal resistance will increase heat transfer in a linear heat conduction experiment when using 2 bars instead of 1. Thank you.
So that is the winning video from the University of Michigan Flint. Now we will find out who their competitor is from the York College of Pennsylvania, and then we will find out which of those 2 have won. So this is York College of Pennsylvania's entry.
Today we're going to show you how we compared 5 friction factor estimation theories for laminar and turbulent flow pipes. This involved using a hydraulic bench to measure the flow rates, velocities, and head losses. For this experiment, our purpose was to determine the best approximation method that can be applied when estimating the friction factor in pipes. This can be applied in the design for smooth pipes, or more accurate use in the greater academia. Results from this experiment will aid in the future use of theories, academics, as well as applications for this type of apparatus. To perform this kind of experiment, we used the TecQuipment friction loss in the pipe apparatus attached to a hydraulic bench. To determine the best approximation method that can be applied to estimating the friction factor, we found the closest fitting relationship to the experimental values. The method includes theoretically calculating the Reynolds number and applying it to the research approximation theories, then determining the closest fitting relationship to the experimental values. one of which we apply for laminar flow and the other floor we apply to using the friction factor determination for turbulent flow. Other than the TecQuipment friction loss in a pipe apparatus attached to a hydraulic bench, we used 1 liter graduated cylinder, 2 stopwatches, a thermometer, and a water collection vessel. 4 variables that we collected when experimenting and collecting data were the temperature, time, volume, and the head loss. As pictured, the H7 apparatus was set up connecting the header tank to the system along with both the inlet and the outlet. Before running tests and collecting data, we made sure to bleed the system to remove all air bubbles from the system, especially in the manometer. Once water moves vertically up the apparatus into the header tank from the inlet pipe, the header tank fills with water, goes down the outlet pipe, and then into the manometer to measure the head loss. After that, the water makes its way to the flexible outlet pipe, which it is then collected by a vessel and dumped into the measure vessel to record the volume. The time is also recorded to calculate the velocity in the system. As you can see here, my finger is following the pipe to show you the flow of water and where it goes throughout the system. For the turbulent flow experiment, we made adjustments to the H7 apparatus by removing the header tank along with its inlet and outlet pipes. For this setup, water immediately runs from the H7 apparatus into the bleed pipes to the manometer, and then from the manometer it leaves through the flexible outlet pipe, where it is then collected by a vessel into a measuring vessel to record the volume. And the time is also recorded to calculate the velocity of the system. As you can see here, my finger follows where the water flows within the system. In each of the listed equations, L is the length of the pipe, H is the head loss, V is the velocity of the fluid, D is the diameter of the pipe, and G is the value of gravity. The theoretical Darcy friction factor for laminar flow is given by Powelly's law. These values are produced with the Pagan-Powelly equation. The friction factor is calculated using the Reynolds number. There are several accepted theoretical equations used to calculate the friction factor, including the Colebrook equation and the Blasius equation. For laminar flow, the experimental friction factor is determined using the Weisbach's equation, derived from the correlation between head loss and pipe dimensions. The von Karman equation assumes that the pipe is absolutely smooth. The co-equation is proposed from his experimental data of turbulent flow in a smooth pipe, largely derived from the Blasius equation. To determine the experimental value of the friction factor, Weisbach's equation will be utilized. The experimental results compared very well to a few of the turbulent flow expected values, with the exception of the von Karman equation. In the results, the 4 approximation methods showed no % error, proving that they are good approximations for a friction factor of turbulent flow. The friction factor for laminar flow using the Pagan-Powelly equation yielded much higher error than expected. With this being a well-accepted equation, the error comes from the experimental friction factor rather than the approximation. The slight downward trend in error suggests that the trials with the lowest flows are most reliable, with the smaller error correlated with the higher Reynolds number. Our graph shows the friction factor versus the Reynolds number for each trial. The graph allows us to analyze the trend line between the laminar and turbulent flow rates. For laminar flow, the result should fit a linear relationship since the Pagan-Powelly equation has a consistent number divided by the Reynolds number. The graph also shows how in turbulent flow rates, the trend line decreases, which means the Reynolds number increases. The friction factor will eventually become constant and independent of the Reynolds number. These findings underscore the importance of carefully selecting the appropriate equations and models when dealing with fluid dynamics in engineering systems.
So that was our winner from York College of Pennsylvania. Now, it's time to find out who our overall winner is. The most important question and the reason we are all here today. So, quick recap. From all the videos submitted, the winners of Heat 1 and the ones who are battling it out for that £1,150 worth of money or Amazon vouchers equivalent and our all-important custom-made trophy are University of Michigan Flint Team 3 and York College of Pennsylvania Team 2. So, the reason we are all here and the crowning winners of this year's Student Competition 2024 Drum roll, please. Congratulations to York College of Pennsylvania Team 2 for their video on friction factor estimation. This means our winners of York College, Pennsylvania Team 2, you will be receiving £1,150 in Amazon vouchers or cash for you to spend how you like, participation certificates, and of course that all-important TecQuipment customized trophy. And this will be shipped to you within the next month or so you can use this and hold it proud and show everyone the hard work that you have done. But I would also like to say congratulations to everyone involved in this year's student competition. We thoroughly enjoyed watching your videos, and we hope that next time, with the feedback and improvement, you can do even better and we can find our next student competition winners. Thank you for joining me today. And again, congratulations to our winners of this year's student competition, York College of Pennsylvania Team 2. Congratulations, thank you for watching, and see you hopefully again this time next year.